In Chapter 5, Section 3, we're going to be looking at enthalpy. So we'll start with the definition of enthalpy, which is not particularly useful at this point, but it is something that we need to look at. And we'll find that enthalpy is defined as the internal energy plus the pressure times the volume. And so like internal energy, enthalpy is a state function. So what that means is that that it doesn't matter what the path is. All that matters is where did you start and where did you end, and that difference between those will give you the change in the enthalpy. So we will find that this, where we take the enthalpy of our products and the enthalpy of our reactants and take the difference between them, that will give us our change in enthalpy. Now, as far as how do we go about determining delta H, well, given our definition that H is equal to the internal energy plus the pressure times the volume, we can get the change in enthalpy by taking the change on both sides. So delta H is equal to delta parentheses E plus PV. And if we look at this, if we do this at constant pressure, then we will get that delta H is equal to delta E plus P delta V. All right. Well, using that equation, the delta H is equal to delta E plus P delta V, if we put the definition for delta E in that we talked about earlier, so delta E is equal to Q plus W, well, we can put in place of that delta E the Q plus W, and we know that W is equal to negative P delta V. So we get this. So, but that's only true at constant pressure, which that is kind of an important point here. So at constant pressure, the delta H is equal to the Q, the heat at constant pressure, minus P delta V plus P delta V. Well, those two P delta V's are going to cancel out, and we will end up getting that delta H is equal to the Q at constant pressure. And that's what the little subscript there means, is that it is at constant pressure. Now, if it's not at constant pressure, let's say it's at constant volume. All right. And we'll deal with that in a second. The change in enthalpy is equal to the heat of the system at constant pressure. And then, like I said, if it's at constant volume, then it's a little bit different, but it's actually even easier to come up with. So what about at constant volume? Well, we know that the change in internal energy is equal to Q plus W, and that W is equal to negative P delta V. Well, if it's at constant volume, that means the volume doesn't change, and so delta V is equal to 0. So that whole part goes to 0. So therefore, delta E will be equal to the Q at constant volume. So enthalpy, delta H, is equal to the Q at constant pressure, and internal energy, delta E, is equal to the Q at constant volume. And here's the thing. Those two numbers are often very close to each other. Let me show you an example of a reaction where we get the delta E and the delta H, and you'll see. So enthalpy and internal energy, their relationship is going to be this. So here we've got an example of sodium reacts with water to give us sodium hydroxide and hydrogen gas. Now, the fact that we're producing hydrogen gas, that is going to increase the volume, so this will do some work on the surroundings. The enthalpy, or the heat that is given off, and because it's at constant pressure, that will be equal to delta H. The heat that is given off is negative 367.5 kilojoules, so it is an exothermic reaction. The change in the pressure volume, so pressure times delta V, is equal to 2.5 kilojoules. All right. So if we have the equation delta E is equal to delta H minus P delta V, we put those numbers in. So negative 367.5 for our delta H, because that's the heat at constant pressure. And then negative 2.5 kilojoules is the negative P delta V. And that gives us a delta E that's negative 370.0. Well, you will see that the value of delta H and delta E are pretty close. That difference is almost negligible. Now, I wouldn't say it's completely negligible, but it is a relatively small number. All right. So now what we want to do is we want to be able to write the enthalpy of a reaction. And we've got some chemical reactions. This is an example of a chemical reaction. Here on the left, we've got hydrogen in a balloon, and then we've got a flame, and presumably there is oxygen around that balloon. When you burst the balloon, the flame will cause the hydrogen to catch on fire, and it will produce water vapor. And in the process of doing that, it gives off quite a bit of heat. Well, we can draw something that is called an enthalpy diagram. And the enthalpy diagram illustrates that the enthalpy of our reactants here, the hydrogen and the oxygen, was much higher than the enthalpy of our products, which is the water vapor. Since it's going down in enthalpy, that difference at constant pressure, that difference is going to be released in the form of heat. All right. So here is an example of an enthalpy of reaction. The change in the enthalpy is going to be equal to the enthalpy of the products minus the enthalpy of the reactants. And again, that's because it's a state function. And so here we have a diagram, and I'm going to use that diagram here just for a second. Before we go to number 33 and 35, I'm going to use that diagram to illustrate a point. All right, so here I have, here we've got the reaction. All right, so the way we can interpret this and write a thermochemical equation is first we could say, well, we've got CH4 gas plus 2 moles of oxygen gas, and that gives us 1 mole of CO2 gas plus 2 moles of H2O, and here it does specify a liquid. Well, that is a chemical equation, and it is a balanced chemical equation. And you'll see the number that is associated with that is delta H is equal to negative 890 kilojoules. All right. Once you put the delta H beside it, that is a thermochemical equation. What that means is if you burn 1 mole of methane in 2 moles of oxygen gas and produce 1 mole of carbon dioxide and 2 moles of liquid water, that the delta H will be negative 890. Now, conversely, we will find if we write the other bit of information we get out of this is that if we take CO2 gas plus 2 H2O liquid and produce CH4 gas plus 2 moles of O2 gas, that there we're going to have a delta H that is equal to positive 890 kilojoules. All right, so that's the other bit of information that we can get out of an enthalpy diagram. So if you have an exothermic reaction where heat is given off, then the enthalpy of our reactants, which is the one that's up on top over here, is going to be higher than the enthalpy of our products, which is the one that's down here. If we have an endothermic reaction, then the enthalpy of our reactants will be lower than the enthalpy of our products. All right, and so that gives us the opposite value. So let's look at number 33 and 35. So I'm going to get rid of that and move this out of the way. We'll look at 33 and 35. So write a balanced thermochemical equation for this reaction. So the complete combustion of acetic acid to form H2O liquid and CO2 gas at constant pressure releases 871.7 kilojoules of heat per mole. All right. The fact that it's at constant pressure means that our heat is going to be equal, then our heat will be equal to the delta H, the enthalpy of the reaction. So let's first start by writing a balanced chemical equation. So we'll do HC2H3O2 liquid plus, since it's burning, that means it's oxygen, O2 gas. And I'm going to go ahead and put some spaces out front so we can balance this. And that gives us carbon dioxide, so CO2 gas, plus H2O liquid. And if you haven't figured it out, it doesn't matter what order we put those in. We could have put the H2O first. Now, as far as balancing this, we'll start by balancing the carbon. So here we've got 2 moles of carbon. We'll balance that, and we'll lock that in place by putting a 2 there, or putting a 1 there, and we'll put a 2 in front of the carbon dioxide. Let's look at the hydrogens. We've got 1 plus 3, so that's 4 hydrogens there. And to get 4 hydrogens out of this, we'll put a 2 in front of water. Now we want to look at this. The total mole, or the total number of oxygen atoms on the right side is going to be 2 times 2, so that's 4 plus 2 more, that's 6. And then over here, we've already got 2, so we only need 4 out of this. So we're going to put a 2 in front of that. All right, and so there we've got a balanced chemical equation. To turn this into a thermochemical equation, all we need to do is to write the delta H value beside it. And so delta H in this case is going to be equal to negative 871.7 kilojoules. And we can write that as kilojoules per mole of this, or we can just write it as kilojoules. I'm going to leave it as kilojoules there. The negative is because it releases that heat. It's an exothermic process. Now, as far as drawing an enthalpy diagram for that, that is pretty straightforward. So when we're doing an enthalpy diagram, we're going to have one thing that's up on top, one thing that's on the bottom. We'll draw a little arrow over here, and that little arrow indicates the increase in enthalpy. Since this is an exothermic reaction, that means that our reactants have a higher enthalpy than our products. It's going down in enthalpy. So we'll put HC2H3O2 liquid plus 2 O2 gas. And then for our products, we've got 2 CO2 gas plus 2 H2O liquid. And then here, I'm going to draw an arrow going down, and we'll put delta H is equal to negative 871.7 kilojoules. All right, and that is an enthalpy diagram. So again, if it's an exothermic process, this one releases heat, it's exothermic, delta H is negative, then you'll have your reactants up on top and your products down on the bottom. If it were endothermic, it would be going the other way. All right, next we're going to draw an enthalpy diagram for this reaction. All right, so again, we'll draw our 2 lines here, and then an arrow indicating that this is the enthalpy. All right, so there's our enthalpy. And since this is an exothermic process, that means our reactants are up on top. So we'll have 2Cl gas. And down on the bottom, we will have Cl2 gas. All right, and then we'll draw our arrow. Again, since it's exothermic, the arrow is going to be pointing down. And we'll have delta H is equal to negative 243.4 kilojoules. All right, once we've done the enthalpy diagram, answering this part of the question is really easy. Which has the higher enthalpy under these conditions, the 2Cl or the Cl2? Well, clearly it's the one that's higher up, so this one has the higher enthalpy. So the 2Cl will have the higher enthalpy. All right, Well, now that we have done the enthalpies of reaction, we want to talk a little bit more about enthalpy and some of the important things you need to remember when we're discussing enthalpy. First of all, enthalpy is an extensive property, and that means that the amount of heat that's given off depends on how much stuff is there. If you burn 1 mole of butane, you're going to get a certain amount of heat. And if you burn 2 moles of butane, you'll get twice as much heat. That's all it means, that it is an extensive property. Second, and we've already seen this, delta H for the reaction in the forward direction is equal in size but opposite in sign to delta H for the reverse reaction. And then next, delta H for reaction depends on the states of the products and the states of the reactants. So the first thing that we want to look at is a couple of rules for thermochemical equations, and these are related to those 3 things that I just showed you. First of all, if you multiply or divide the coefficients of the reaction, then you need to do the same thing for the corresponding delta H. So for example, what this thermochemical equation as written means is if you combine 1 mole of nitrogen gas, 3 moles of hydrogen gas to make 2 moles of ammonia gas, it will release 91.8 kilojoules of heat at constant pressure. However, if you double the coefficients, so you take 2 moles of nitrogen gas plus 6 moles of hydrogen, and you get 4 moles of ammonia, then it's going to release twice as much heat. So the delta H will be twice as big. So that's one thing that we want to remember. And you don't necessarily have to choose a certain number. You don't have to choose an even number of moles or an integer number here. So now I'll show you how we deal with that here in just a few minutes. All right. If you reverse the direction of a reaction, then you need to change the sign of delta H. And we saw this a minute ago when we looked at those 2 thermochemical equation, the examples. But here, if we take the nitrogen plus hydrogen gives us ammonia, and we change the direction, so 2 moles of ammonia decomposes to give us 1 mole of nitrogen and 3 moles of hydrogen, it has a delta H of positive 91.8. So we just change the sign of delta H. All right. Our third factor is about the states, and the states matter. So notice the difference here between these 2 reactions at 25 degrees Celsius. So here we've got hydrogen plus oxygen gives us water vapor. That has a delta H of negative 483.7. And here we've got what looks like the same reaction, but you'll notice the difference is that it says liquid water, and it has a delta H of negative 571.7. Well, that's a difference of 88 kilojoules. So that's a difference of 88 kilojoules. Now, there's something I'm going to do here, which is actually talking about a concept that we're going to be using here in a little bit called Hess's law, which is that we can take equations, add them together, cancel out the things that are the same, and it will give us the delta H for a new reaction. We'll practice that here in a bit, but let's just take that first reaction as it is and leave it as it is. But we're going to take the second equation here, and we're going to change the direction of the reaction. Remember, when we change the direction of the reaction, we need to change the sign as well. So here we have 2 H2O liquid will decompose to give us 2 moles of hydrogen gas and 1 mole of oxygen gas. All right, and of course we change the sign of delta H. All right, so we can add those 2 equations together, and when we do, we're going to cancel out the 2 moles of hydrogen gas and the 1 mole of oxygen gas, and we're going to be left with 2 moles of H2O liquid gets converted into 2 moles of H2O gas, and it has a delta H of 88.0 kilojoules. All right, so this isn't even a chemical reaction. This is a process. It is a physical process. It's water evaporating. So at 25 degrees Celsius, we would find that if we want to evaporate 2 moles of water, we would have to add 88 kilojoules of energy. Now, in a very similar fashion to what we did with Rule 1, is if we don't want these 2 moles here, we want it, let's say we wanted this per 1 mole, well, then we could divide that by 2, but we need to divide this by 2 as well. And since now we have 1 mole of water getting converted into 1 mole of water vapor, we can do this as positive 44.0 kilojoules per mole. When you make this per mole, you can turn your enthalpy from an extensive property into an intensive property because now it is listed as per mole. So that means that if we want to take 18 grams of water, 1 mole of water, and evaporate it at 25 degrees Celsius, 44 kilojoules of energy needs to flow into that water for the evaporation to occur. In case you're curious, that is roughly equivalent to 296 Randy Johnson fastballs, my favorite unit of energy. All right, well, let's look at problems 38, 43, and 45. And these are a little bit longer problems, and they involve some calculations, so they are a little bit more time-consuming than the other ones, but not too bad. All right, so I get my calculator on the screen there. All right, so number 38 here says, consider the following reaction. We've got 1 mole of CH3OH gas gives us 1 mole of CO gas plus 2 moles of hydrogen gas. All right, and that has a delta H of positive 90.7. Now, assuming that we're doing this at constant pressure, then that is also going to be the heat. And the question, part A, is heat absorbed or evolved in the course of this? Well, since it's positive here, that means it is endothermic, so heat is absorbed. All right, and that is because delta H is greater than 0. So next it says, calculate the amount of heat transferred when 45 grams of CH3OH gas is decomposed by this reaction at constant pressure. All right, when we're doing this, we're going to do a roadmap. And so the quantity that we know is the mass of CH3OH, right? Because we have 45 grams of the CH3OH. We're going to convert that into the moles of CH3OH, mass to moles, use molar mass. And then to convert from the moles to the heat, we're going to do this. So the moles to the heat. All right. And to do that, we're going to do, it's kind of like when we do moles to moles and we do the ratio. Well, here, we're going to do the ratio of this delta H to whatever the coefficient is. In this case, the coefficients are 1, or at least the coefficient for that one is 1. So, so let's go ahead and set this up. All right, so 45.0 grams of CH3OH. And we want to convert from mass to moles. We want to use the molar mass. Let's see. Let's go ahead, clear all that. We've got, what have we got? We've got 1 carbon, so 12.01 plus 4 hydrogens. So 4 times 1.01 plus an oxygen, which is 16.00. And we add that all in there, we get 32.05. So 32.05 grams of CH3OH per mole of CH3OH. All right, so that gets us from mass to moles. You'll see grams of CH3OH cancels out. Now we want to go from moles to heat. Moles to heat, we're going to use the ratio, and the ratio here is the ratio of this number to that coefficient. So that will be positive 90.7 kilojoules per, per 1 mole of CH3OH. And you'll see moles of CH3OH cancels out. All right, so we'll do 45.0 divided by 32.05. All right, and then we're going to multiply that number by 90.7. And with 3 sig figs, we'll call that 127 kilojoules. All right. So for a given sample of CH3OH, the enthalpy change in the reaction is 18.5 kilojoules. How many grams of hydrogen gas are produced? Again, we're going to set up a little mini roadmap here to figure this out. We know the heat, that's the quantity that we're starting with, is the heat. And we're going to convert from the heat, and since we're going here to hydrogen, we'll do the moles of hydrogen. And then from the moles of hydrogen, we'll go to the mass of hydrogen. All right, from heat to moles, we're going to use the coefficients. All right, so we'll do 18.7 kilojoules. And we want the ratio of moles of hydrogen to the heat. So that's going to be 2 moles of hydrogen for every 90.7 kilojoules. So 2 moles of hydrogen for every 90.7 kilojoules. And that is a positive quantity there. All right, next we want to go from moles of hydrogen to the mass of hydrogen. Moles to mass, we'll use the molar mass. The molar mass of hydrogen, so H2 is 2.02. So 2.02 grams of hydrogen per mole of hydrogen. And that's it. So we'll do 18.7 times 2 times 2.02, and then we'll divide by 90.7. And that gives us, again, 3 sig figs here, so that gives us, I feel like I put something in correctly. I put in the wrong number here. I'm glad I found that, because otherwise I would have been really confused. So this should have been 18.5. So let me fix that real quick. It just shows you that it's so easy to make a mistake here. So that's 18.5. So here, I'm going to clear all that. Let's try that again. 18.5 divided by 90.7. And we'll hit enter, and then we're going to multiply by 2 and multiply by 2.02, and we get 0.824. So 0.824 grams of hydrogen should be produced. All right, what is the value for delta H for the reverse of the previous reaction? So delta H for our reverse of the reaction. Well, delta H for the reverse, let's go ahead and rewrite the equation. So we have CO gas plus 2H2 gas, and that's going to give us CH3OH gas. And when we reverse the direction, we'll change the sign. So that'll become negative 90.7 kilojoules. So that's the delta H for the reverse reaction. Now, how many kilojoules? So we're looking for heat. How many kilojoules of heat are released when 27.0 grams of CO reacts completely? So the quantity that we know here is the mass of CO, and we want to convert to the kilojoules. So again, I'm going to write out a roadmap here. So our mass of CO, and we want to convert from the mass to the moles of CO, and then from the moles to the heat. So our mass of carbon monoxide that was listed here is 27.0 grams of CO. All right, we're going to multiply that, or divide by the molar mass. And the molar mass comes out to 28.01 grams of carbon monoxide per mole of carbon monoxide. Okay. Then, so that gets us from mass to moles. Moles to heat, we'll want the ratio of this delta H to the moles of carbon monoxide. So that's going to be negative 90.7 kilojoules per 1 mole of carbon monoxide. And you'll see grams of carbon monoxide and moles of carbon monoxide cancel out, and that's going to give us our kilojoules. So we'll clear all that. We'll do 27.0 times negative 90.7. And then we're going to divide that by 28.01. And you'll see the number that we get there, it is negative. So negative 87.4 kilojoules. So negative 87.4 kilojoules. All right. So that's number 38. We also want to do number 43 and 45. So let's look at 43 here. We'll read through this. A gas is confined to a cylinder under constant atmospheric pressure, as illustrated in the figure below. All right, so kind of like what we saw in the lecture. When the gas undergoes a particular chemical reaction, it releases 79 kilojoules of heat to its surroundings and does 18 kilojoules of pressure volume work on its surroundings. What are the values of delta H and delta E for this process? Well, first of all, since it is at constant pressure, then the heat is going to be equal to delta H. So delta H, quite easily here, is going to be negative 79 kilojoules. So negative 79 kilojoules because it released. For delta E is equal to Q plus W, and we just wrote down what Q was because Q is the heat. It's at constant pressure. So negative 79 kilojoules. And then the work, since it's doing work on the surroundings, then that number is going to be negative, and so we'll have negative 18 kilojoules there. So negative 79 minus 18, we don't even need a calculator there. That's going to be negative 97 kilojoules. So delta E will be equal to negative 97. So that one turned out pretty easy. All right. For this last one, this is a little bit trickier. All right, so it's a little bit trickier, but it is not too bad. All right, the only part that's really tricky is this last thing. So here it says, what is the consider this equation. So we've got CH3 and 1.5 moles of oxygen, and that gives us CO2 gas plus 2 H2O liquid, and we have this value of negative 726.5 kilojoules. So what is the enthalpy change for the reverse reaction? Well, that's easy. We just change the sign. So delta H for, I'm going to put reverse, is going to be equal to positive 726.5 kilojoules. Again, when we change the direction, we just change the sign of delta H. Now we want to balance the forward reaction with whole number coefficients. So what is delta H for the reaction represented by this equation? So let's take that reaction, and to get rid of this fraction, we're going to multiply everything through by 2. So we'll end up with 2 CH3OH liquid plus 3 O2 gas, 2 CO2 gas, and 4 H2O liquid. And then delta H, since we doubled the value of that, we're going to double that delta H. So we'll do 2 times 726.5, and I should have made that negative. Try that again, negative 726.5. And so that's going to come out to negative 1453 kilojoules. All right, next, which is more likely to be thermodynamically favored, the forward reaction or the reverse reaction? So this is one of those things, and we haven't talked about this yet, but it turns out that most of the time, exothermic reactions tend to be more favorable than endothermic reactions. In this case, it's easier to burn methanol and convert it into carbon dioxide than it is to take carbon dioxide and water and unburn it and turn it into methanol. So we will find that exothermic reactions tend to be more favorable. So we're going to say the forward reaction is more favorable because it is exothermic. Now, why that's true, why exothermic reactions tend to be more favorable? Well, there's something that we haven't talked about yet that's called the second law of thermodynamics. And the second law of thermodynamics tells us, in general, that energy likes to spread out. So when heat is given off from a reaction, then energy generally will spread out. Now, that doesn't mean that it's impossible to do the reverse. It just means that it is more difficult. All right. So now, let me scoot this up a little bit here. All right, so it says, if the reaction were written to produce H2O gas instead of H2O liquid, what would you expect the magnitude, or would you expect the magnitude of delta H to increase, decrease, or stay the same? Well, rather than guess, let's think it through. We're going to draw an enthalpy diagram for the reaction as it is written. So here, this is our enthalpy. All right, so enthalpy got a little sideways there. And since this was an exothermic, we'll use this one here. Since this is an exothermic reaction, we have 2CH3OH. Because it's exothermic, our reactants are going to go up on top. So 2CH3OH plus 3 O2 gas. And then down here on the bottom, we've got 2 CO2 gas plus 4 H2O liquid. And we know that that particular reaction had a delta H that was equal to negative 1453 kilojoules. Okay, so if we've got instead where H2O gas is our product, that means that the energy or the enthalpy level of our product is going to be higher. The enthalpy level of our reactant will be exactly the same. So I'm going to draw this one exactly at the same place, but the enthalpy level of our product is going to be higher. And the reason for that is when you convert, and I'm not going to make it too dramatic, but you can see that this is higher. And the reason is when you convert H2O liquid into H2O gas, you have to add energy to make that happen. So this is going to go up. So that is going up in energy. So we'll put the values in there. So CH3OH liquid plus 3 O2 gas. And then what's different here is our product. So 2 CO2 gas plus 4 H2O gas. And again, the gas is higher in enthalpy than the liquid. You have to add energy, you have to add heat to convert that liquid into the gas phase. All right. So we saw a little earlier that the value for H2O liquid going to H2O gas, in fact here, I'm going to switch over here. That value for going from H2O liquid to H2O gas is 44.0 kilojoules per mole. Since we have 4 moles here of water, we're going to add 44 kilojoules times 4 to this. So 4 times 44. So we're going to take that negative 1453 and we're going to add 4 times 44. And that gives us a delta H that is equal to negative 1277 kilojoules. So now answering the question, would you expect the magnitude? And magnitude is just the absolute value. So magnitude of delta H to increase, decrease, or stay the same. Well, it got smaller, so the magnitude decreased. And that's why that is. All right. And we're going to stop the video there, and we'll do calorimetry and Hess's law and enthalpies formation. We're going to do that on the next video.